let's review what we know so far about the first derivative test. Right, this is what your quiz was over, and we've been talking about the first derivative test for a little bit. But just to kind of remind you, what the first derivative test does is it gives us a way of locating extrema and classifying them using the first derivative. So let's just look through a quick example here to see how that'll work. So if we have 5x to the fourth minus x to the fifth, we're going to find the derivative, the first derivative, and we can do that using the power rule. So first derivative would be 20x cubed minus 5x to the fourth. And then we want to find the critical values of f. And we do that by finding the x values where the derivative is either 0 or undefined. So if we set this thing equal to 0, so 0 equals 20x cubed minus 5x to the fourth. We can factor out a 20x cubed there to solve this. 20x cubed times, not 20x cubed, 5x cubed, sorry. 4 minus x. So where are the two critical values here? What x values make this equation 0? Yeah, 4 and 0. So these two numbers are our critical values, and these are locations where we potentially have a local extreme. So these two right here are our critical values. And so to determine, using the first derivative test, whether we have maxima, minima, or maybe neither, we're going to create a little sign chart, labeling those critical values on our sign chart. And then we can pick a representative from each interval, plug it into that factored form, and find out whether or not the derivative is positive or negative. If the derivative is positive, we know that the function f is increasing. If the derivative is negative, we know the function f is decreasing. And if we have a sign change, if it goes from negative to positive or positive to negative, that's where we have an extreme. And depending on which way it goes, will tell us if it's a max or a min. If the sign doesn't change, then although we do have a horizontal tangent line, there will not be a local extreme value. So we can plug in numbers like like -5. If we plug that in here, we're going to get a negative times a positive. So that would be negative. Okay, in other words, the derivative is less than 0. If we plug in a number like 1, and zoom in here so you can see this a little easier. If we plug in a number like 1, we're going to get a positive times a positive is positive. And if we plug in a number like 10, we get a positive times a negative, which is negative. Now this is a number line for f prime. I'm going to label that because today we're going to get into what the second derivative can tell us. So on f, maybe we'll make like a separate number line here with 0 and 4. So on f, if we know that the derivative is negative, how can we classify what's happening to f in that interval? Like what word do we use to describe f if the derivative or the slope is negative? Yeah. Decreasing. Yeah, so f is decreasing in that interval. It's also decreasing from 4 to infinity, and it's increasing between 0 and 4. So this is how the values of f and f prime are related. Okay, so to answer these questions, I guess let's start with the increasing, decreasing interval since we have all that labeled already. We have two increasing intervals. We've got an increasing interval, or no, I'm sorry, we have one increasing interval, and that's between 0 and 4. We have two decreasing intervals, one between negative infinity and 0, and then the other one is from 4 to infinity. Any questions so far? I know this is all review, but I think it's good to kind of go back over this, especially considering what we're about to do. Okay, so the other thing that the first derivative test does, and really this is kind of the whole point, is not only can we analyze what's going on with the slopes of f using these critical values, but we can also use it to find the local extremes. If the slope changes from negative to positive, so it starts negative, then goes positive, or I guess maybe I should draw that on f and not on f prime. So on f, the slope's going from negative to positive. So we can say that at x equals 0, we have a local minimum. So we have a local minimum at 0 comma something. And we'll come back to find the y value here in a second. If we think about what's happening on the graph of f prime, the value of f prime is changing from being negative to being positive. So that means at 0, the graph of f prime has an x-intercept at 0, and the graph is going from below the x-axis to above the x-axis. Just to give you a little glimpse as far as what we should be seeing in that graph. Now, when the slope of f changes from increasing to decreasing, so if we go from an increasing slope to a decreasing slope, at that point, we're going to have a relative maximum. So we're going to have a relative maximum at 4 comma something. And if we are going to examine what's happening on the graph of f prime, we have an x-intercept at 4, and the value of f prime is changing from positive to negative, so we should be going from above the x-axis to below the x-axis. Now, you had to do this on the quiz last time. This isn't really, and maybe on the homework, I actually don't even really remember, but let's see if you guys kind of remember from at least the quiz, how do we find, or no, I think there was a quiz question, now I'm thinking about it. How did we find the y-coordinate of the relative extreme values? Where are we going to grab those from? Yeah, so now the real question here is which one do we plug it into, right? So if I have a graph of f and it's got a relative minimum, we know we have a relative minimum at 0 here. So I've got some graph, it's doing something like this, I don't know. And we want to find the y-coordinate of this point. To find the y-coordinate of this point, we want to plug it into this function, into the function f. All right, so let's do that. So if we plug in 0 into the original function f, so we're just plugging it in here, find f of 0. Maybe I'll write that out just so if you're looking back at this, you can see where we got this number. Oops. Is f of 0. And so if I plug in 0, just get 0 minus 0 is 0. Yeah. So the y-coordinate is 0. So we have a local or a relative minimum at 0, 0, and we know there's a local minimum because, I'll just make a little point here, that the derivative f prime went from being negative to positive. A local maximum is going to occur when f prime goes from positive to negative. Now, this one, I think finding the y coordinate is not really going to be reasonable to do by hand. So just because like you'd have to do 4 to the 5th power, I don't think that's particularly reasonable. So I'm going to sort of cheat here, use a calculator. Yeah, I don't think that's not one that I think on the AP test they're going to ask you to do by hand. So 5x, 5 times 4 to the 4th minus 4 to the 5th is 256. Right, and I'm getting that from plugging in 4 into x. Now, I wouldn't expect you, like on a non-calculator, to be able to compute that. That's a little bit, I think, beyond what would be reasonable. Okay, so we got the coordinates of the relative extrema. It's at 0, 0, and that's because the derivative went from negative to positive. And we got the coordinates of the relative maximum, which happens when the derivative goes from positive to negative. We have an increasing interval between 0 and 4, okay? And it's increasing there because f prime is positive, okay? And the decreasing intervals happen when f prime is negative. So all of this is really all the information that we can get from using the first derivative test. It's a test on the first derivative to find where the function's increasing, decreasing, and also to find the relative extrema. Does anyone have any questions before we start going over the new stuff? All right. So before we really get into what the second derivative test is, I want to lay out some new vocabulary terms for you. The first word being concavity. Okay, when you have a graph that's doing stuff like this, right? There are different intervals on the graph that we're going to consider being concave up versus being concave down. Okay, concave up is going to be when you have like a valley. Okay, so like somewhere like between here and here, say, would be concave up. Okay, it's like making like a U shape. Like a parabola is always concave up. If the curve is like going downwards, like forming like a hill, so to speak, where you would find like a local maximum, this would be concave down. Now, finding these points where the graph is changing from being concave up to concave down, or vice versa, these points are called points of inflection. Okay, so we're going to go through all this. I just want to give you just generally what these terms mean. But let's be a little bit more specific here. Okay, the graph of a function is concave up if, not f, but f prime is increasing. F prime is increasing. If f prime is increasing, what does that tell you about f double prime?
Positive.
It's
be a straight line. Or, well, no, increasing could be
what does it mean if f is increasing? If f is increasing, what does that tell you about f prime?
that it's also increasing. It's on the positive.
Not necessarily increasing.
Or a straight line.
So, could be, but more importantly, it's positive. Okay? So, if f is increasing, if f's going up, the derivative, f prime, the slope, is positive, right? So, if f prime is increasing, think about it like this. If f prime is the velocity and it's increasing, you're getting faster. Another way of describing like getting faster is you're accelerating. The rate of change is positive. So if f is increasing, f prime is positive. If f prime is increasing, that means that f double prime is positive. Oops. So anywhere that f double prime is positive, the original graph f is concave up. Okay. If f prime is, oops, we got a typo here. Decreasing. Let's change this. Decreasing. So if f prime is decreasing, f double prime is negative. Now, just like we have a critical point anytime f prime is 0 or undefined, we have what's called a subcritical point anytime f double prime is 0 or undefined. Now, whenever that happens, if there is a sign change, we have what's called a point of inflection. Okay, this could be the signs changing from positive to negative, meaning it's changing from being concave up to concave down. Or it could be the other way. It could be switching from concave down to concave up. Okay, so concave up, is going to be something like this. Concave down is going to be something like that. A point of inflection is when we change concavity. So if you have a graph that's doing something like this point right here where the concavity changes, that's the point of inflection. So when we're trying to justify our answers about the second derivative stuff, just like how we said, oh, we know there's a relative max at x equals 4 because f prime went from positive to negative. We could also make similar statements like, oh, we know there's a point of inflection at this point because f double prime went from positive to negative. Or just, you could simply say a change sign. Now, what's kind of nice here, and we'll get into this in a minute, is they're using the second derivative. You can actually find points where you have relative extrema a little easier than creating a sign chart using the first derivative. I'm going to show you how to do that in a minute. But first, let's just practice with this function that we had above. And let's see if we cannot find at least the x value where we have a point of inflection on this graph. Okay, so we're going to describe the concavity of this same function we're just dealing with. And we're going to find where the point of inflection is. So first, we're going to find the first derivative, and we already did that above. Okay, we know that's 20x cubed minus 5x to the fourth. F double prime then would be 60x squared minus 20x cubed. I'm just using power rule here. So if I want to find a point of inflection, I need to figure out what my subcritical values are. The subcritical values are where the second derivative is 0 or undefined. Now, this is a polynomial. It's not ever going to be undefined, so we just need to be concerned with where it is 0. So we'll set this second derivative equal to 0. We'll solve it just like we solved the first derivative equal to 0. It's the same technique here, where we're going to factor out a GCF, which in this case would be 20x squared. You could also just divide both sides by 20 to simplify it, but either way is fine. So 20x squared times 3 minus x. So I get two subcritical points, one at 0 and one at 3. Okay. So once you find your subcritical points, we're going to create a sign chart. This is going to be for F double prime. And we're going to be looking at the sign, whether this function's positive or negative, in between and surrounding these subcritical points at 0 and at 3. If we plug in a number like -1, we're going to get a, now this is squared, this 20x squared is just always going to be positive, so we can safely ignore that. So if we do 3 minus -1, that's going to be positive. If we plug in a number like 1, 3 minus 1 is also positive, so we do not have a sign change there, meaning there's no point of inflection. And then we have, if we plug in a number like 10, we get a negative value. So there's only one point of inflection here, and it's at x equals 3. All right. We can also, using the sign chart, determine where the graph of f is concave up or concave down. It'll be concave up if the second derivative is positive, and concave down where it's negative. So between negative infinity and 3, the graph is concave up, and between 3 and infinity, the graph is concave down. Now, with all this information between the first derivative test and the second, we haven't really defined the second derivative test, but we're kind of using it already, we can construct a pretty respectable graph of f at this point. So let's see what kind of information do we know about f. So here's my graph. Let's go back to what we know about the first derivative test. Okay, we know we have a relative minimum at 0, 0. Right, so we know we have a point here. We know we have a relative maximum at 4, 256. So this is obviously not going to be to scale, but I'll put 4 here and 256 up here. We know that the slope of this graph from negative infinity to 0 is negative, because we found the first derivative to be negative there. So the graph is going to have a negative slope here. It's going to have a positive slope in between 0 and 4. And then a negative slope afterwards. Now, you might be wondering, okay, so all that I was able to sketch that out just with the stuff from the first derivative test. But what the second derivative test tells you, or what it will tell us eventually, is where are our intervals of concavity? In other words, where exactly between 0 and 4 does our second derivative change sign? So we just solved that, right? We found that happens at x equals 3. So at this point is where the graph switches from being concave up to concave down. And we could plug in 3 if we want to know exactly what that point was. But yeah, any questions so far? All right, so just to summarize what we found here, we have a point of, let me summarize it like this. We've got an interval where the function is concave up between negative infinity and 3. It's concave down between 3 and infinity. and we have a point of inflection at x equals 3. Now, what's kind of interesting here is that if we know that the first derivative is 0, oh, yes, ma'am, yes.
Is 4 not like an x-intercept?
So 4 is an x-intercept of f prime, of the first derivative. So if we're, I guess I should have labeled this. This is the graph of f, not f prime. So you will have an x-intercept on f prime. What we're seeing on f is a local maximum because the slope is 0. That's why you have an x-intercept on f prime, is because the value of f prime is equal to the slope of f. So right here, the slope is 0, and therefore, if we were to graph f prime, and that's kind of what we're moving towards, is like, okay, let's graph f prime, and f double prime. Yeah, we're getting there. We're getting there. But yeah, so anyway, does that clear that up a little bit? Yeah.
If you were going to try to find the y value of the
Mhm.
point of inflection, would you plug it into the equation for the second derivative?
Neither to f. Yeah. So like, yeah, if we want to find like where that is, we would it would be at let's just find where it is. 3, comma, and then this would be like f of 3. Okay, so this is probably going to be another calculator problem here, but if we plug in 3, we got 5 times 3 to the 4th minus 3 to the 5th, so it'd be 162. So this point right here, yeah, would be 162. So you're going to use the function that you're trying to graph. Just whenever you're trying to find any y coordinate for anything, if you're trying to graph f, you're going to plug it into f. If you're trying to graph f prime, you plug it into f prime. If you're trying to find f double prime, plug it into f double prime. Yeah. So just substitute it into the function that you're interested in graphing. Yeah. So what we're using here, we're actually using the second derivative test, even if I haven't like spelled out what the second derivative test is, but it's very similar here to the first derivative test, and actually is kind of a useful way of finding these local extrema. Because previously what we had to do is we found our critical values, right? Like up here, we found our critical values at 0, 4. We created our sign chart and tried to find where the function's changing from being having a positive slope to a negative slope or vice versa. But if we have something like this, if we have a local minimum where the slope's changing from negative to positive, this whole like U-shaped looking thing is a place on the graph where the function is concave up. So if we can determine where the function's concave up, if we know the slope, if f prime 0 on a concave up interval, then it has to be a minimum. If we find that the slope is 0 where the function's concave down, then we know we have a maximum. And this is basically what the second derivative test says, is that if f prime is 0, then you can find relative minima and maxima without making the sign chart. You don't have to check the sign of f prime. Instead, just find f double prime, and if it's positive at that location, then you know you're going to have a minimum because it's concave up. Okay, if f double prime is positive, this means that we are concave up, right? In other words, like the graph is making like a U-looking shape. And if the second derivative is negative, then we know that the function's concave down, and therefore, if the first derivative is 0, then we have a relative maximum at that point. So it seems like, you know, when I first learned about the second derivative test, at first I was like, well, how does that help us at all? Like, we already have a way to find these relative extrema. But this is kind of nice if the f prime is hard to evaluate, right? Like if you've got to do like 5 to the 5th power and you don't have a calculator, that's pretty tough to do. Like, I mean, you could probably make it happen, but it's a little tedious and, not very nice. So what you can do instead is find the second derivative, figure out whether or not the second derivative is positive or negative, and then you'll know if it's a max or a min. So it does have its place. So let's kind of summarize what we are going to see on these graphs here. So I'm going to just make a little diagram over here. So if you have a graph that's doing something like this or something like this, for both of those, do those represent intervals where our graph is concave up or concave down? Let's start with that. On either one of these, they're both the same. But these are concave up, right? So if you see a piece of the graph that looks like either one of these, we know that the second derivative is positive, right? However, if we see a piece that's going downwards from left to right, that's got a negative slope, and therefore the first derivative is negative. If the slope is increasing, the first derivative is positive. So now we're starting to put together, okay, well, if we know what the sign of the first derivative is, and we know the sign of the second derivative, we can really get a good idea of what the graph should look like. Now, similarly, if we have pieces that look like this, in both of these two cases, these are both concave down, and so the second derivative is negative. But the first derivative is about the slope of the function. And in the first, this one on the bottom left, the slope is positive. One on the right over here, the slope is negative. So these are all the combinations. Now, if the first derivative is 0, we've got a horizontal tangent line. We have a whole process using the first or second derivative test to determine what's happening there. It's either the point where we have a maximum or minimum. And if the second derivative is negative, we potentially have a concavity change from being concave up to concave down. Any questions so far? Okay. I'm just getting warmed up here. Yeah. All right, let's take a look at this graph. What I really want to do is break down f prime, and f double prime. Okay, let's start with f. This is the graph of f. Where is f positive? How can you describe where f is positive here?
Above the x-axis?
Yeah, above the x-axis. Good. So yeah, f is positive here, right? F is negative here. So that's f. That's everything you learned before calculus. Yeah. So now let's bring in what we know about, calculus-wise. So let's start with the first derivative. When is the first derivative positive? Or don't give me the intervals, just in general. How do I know if the first derivative is positive? Yeah, Peyton, what do you think? When the function's increasing. So what are we looking at? How do we know if the function's increasing?
You can look at the concavity. The slope is positive.
When the slope is positive. Okay? We can't determine concavity unless we know information about the second derivative. Okay, so like from -9 to -6, we can say that here in this interval, the derivative, f prime, is negative. From -6 to 3, the derivative is positive. Right? You can see the slope's going up. It's increasing. From -3 to, looks like 1, we have a negative first derivative. from 1 and really all the way to 9. Actually, I'll put a little break here at 6 because it does go to 0 momentarily. But we'll say that overall, the slope here is positive. Or actually, you know what? I kind of want to break that up. Let's separate those intervals. Now, what's happening? What is the value of f at every partition here?
0.
It's 0. Yes, good. Okay. So yeah, it equals 0. So f equals 0 here, equals 0 here, equals 0 here, and here. What is the value of, oh, I'm sorry, that should be f prime. What is the value of f prime at the endpoints? It's undefined. Okay, so yeah, f prime is undefined. F prime, undefined. Okay. So that's all the information that the first derivative test is going to give us. Second derivative test, now we're going to look at this. Oh, yes, sir. Yeah. Did I miss one? Yes. The derivative equals 0.
Oh, I mean like x. Oh wait,
Yeah. I know this is going to get pretty cluttered pretty quickly. But basically, I'm just saying that at these partitions of the domain where we have either local extrema or really just horizontal tangents, the derivative is going to be 0. Now let's talk about the second derivative test. What does the second derivative tell us about this function? What do we know about the second derivative based on what we see here? Now, finding the points of inflection takes a little bit of algebra. So I've just kind of circled, roughly where they are. I didn't really even do the math here, but we're going to say that these circled points are going to be, this one's probably going to be up here. Now I'm looking at this a little closer, but we'll just say those circled points are the points of inflection. Okay, these are the points where the concavity is changing. And again, we probably need to do some algebra to know exactly where they are, but this will be, overall should be okay. So if the function's concave up, so like between -9 and 5, if the function's concave up, the second derivative is positive. If the function's concave down, so here, maybe I can highlight this to really send the point here. So that's where it's concave up. It's going to be concave down here. Okay, so from -5 to, looks like -1.5-ish. Let's not be too concerned about the actual values here. Just want to get the concept down. The second derivative is negative. Between -1.5 and it looks like roughly I'm going to call it pi because it's like right past 3. I don't know. The second derivative is positive. We can see that the graph is concave up here. Then from 3, or about 3.1, I'll just call it pi, to about 6, we have another interval where the graph is concave down. So the second derivative is going to be negative. And then between 6 and 9, we have another interval where our graph is concave up. There we go. All right, so from here to about here, the second derivative is positive. Any questions so far? Okay, so let's see. We totally analyze this. Oh, one other thing. What about these points of inflection here, where the concavity changes? What do we know about f double prime?
Is that where they equal 0?
It's where it equals 0, exactly. So these partitions of these intervals is where the second derivative is 0. So second derivative of 0 is here, second derivative of 0 is here. Really all these points of inflection. So we have our first derivative test, second derivative test. They're both giving us information about f. Okay. We kind of overanalyzed this, but I just wanted you to see exactly how the first and second derivative are related to the graph of f. And now these follow-up questions should be pretty easy because they're just asking if it's positive or negative. Okay, so at -4, is f positive or negative? Or 0? Yeah, it's positive. Yeah. Now we could see at -4, the value of f is positive. At 1, is it positive, negative, or 0? Yeah, it's negative. Because we can see at x equals 1, the value of f is below the x-axis. At 6, you can see the value of the function is above the x-axis and therefore positive. Oh, wait, did I say less than 1? Why did I write that? Let's fix that. Less than 0. All right, so now we'll talk about the first derivative. At we'll go back to -4 here. First derivative. Is first derivative positive or negative here? So in other words, is the slope positive or negative?
Slope is positive.
Slope's positive, so first derivative is positive. At 1, what's going on with the slope? It's 0. We have a relative minimum there. At 6, what's the slope here? 0. Yeah, 0 again. All right, now let's talk second derivative. At -4, the graph is concave down. So what do we know about the second derivative? It's negative. Good. Less than 0. Yeah. Not less than 1, right? At 1, concave up. So the second derivative is positive. And then finally at 6, what can we say about the second derivative? 0, because that's where the sign is changing. Very good. All right.